So, this is one of the lectures in which we want to summarize what we had been teaching through TA classes on how we can put different concepts together and tie it up and see how it falls in bigger with the under the bigger umbrella of mathematical aspects of biomedical electronic system design, isn't it. So, let us go through some of the slides today. You have been learning in this course a lot of math, right, and at the side you are also learning on several design and fabrication of sensors, and you are also learning on application of sensors and electronic systems, and then we are merging how to use the math to help to form the modeling, and that will help finally to in simulation, followed by fabrication, followed by electronic system design, and then application of this particular product, right. So, that makes the complete circle. Circle can be this, right, not like this, but the point is how we are connecting each dot and how it will be useful and what are the next step that one can move or take after understanding this particular course. So, that was the idea. If you see the slide, in this slide you can see that when we talk about biomedical electronic system design, which is right over here, right, in the center, you are talking about sensor fabrication and characterization, you are talking about multiphysics and electronic simulations, you are talking about signal conditioning circuits and associated electronics, you are also talking about packaging of that comes under system embodiment design, there is system integration and validation. Finally, there is a mathematical analysis that makes this entire biomedical electronic system design, and that is why understanding the concepts of math for this particular research as well as this particular domain is very important, right. So, in this we have looked into several techniques. So, I will just go through some of the slides in which you will just understand or revisit the topics that we have been discussing. So, the first one is the thermal evaporation system. We understood that by heating the metal or a material in the boat, right, it gets melted, and when it gets melted it gets evaporated, and that it evaporates and deposits on the substrate. Substrate can be silicon, substrate can be glass, substrate can be polymer. Everything falls under vacuum, so it is also called vacuum deposition. Then we have seen E-beam evaporation. E-beam evaporation is used when the material that you are using for evaporation has a higher melting point than the material of the boat, right, because if the material has a higher melting point than that of boat, you cannot melt it in thermal evaporation. So, in that case we use crucible and then we use the electron beam to focus on the material. There are multiple ways of indenting the beam like point source or scanning, right, or triangulation. But in any case, the point is that using the electron beam we can melt the material and the material will deposit on the substrate. The third one that we have seen under the vacuum deposition is this sputtering. Sputtering is a mechanical way of dislodging the atoms from the material, and those would be deposited onto the surface, right. That is using the argon gas, and the substrate is at anode and the this target is at cathode, and when we apply a voltage there is DC sputtering, or if you apply RF then is a RF sputtering. There is a magnetron that can improve the rate of deposition, also uniformity of the deposition, right. So, this all three things, thermal evaporation, electron beam evaporation and sputtering, this falls under thin film deposition or PVD, which is called physical vapor deposition. Then we have seen another part of the thin film deposition which is called chemical vapor deposition, and in chemical vapor deposition you have seen several different kind of chemical vapor deposition. Some of the things are discussed in this course, some of the things are not. If it is not discussed in the course, please look into the several books. It is already given in the reference list. You can look in the Google, you can look at the previous courses in NPTEL which talks on sensor fabrication, which talks on clinical perspectives, which talks on op amps, right, and you will see that at some courses, thin film deposition courses, there will be talking about LPCVD, PECVD, MOCVD, APCVD, thermal ALD, and PEALD. So, as you know that CVD stands for chemical vapor deposition. When you say LP is low pressure, P is plasma enhance, then metal oxide, atomic process, CVD. So, different kind of and then atomic layer deposition is thermal ALD. So, several ways or several techniques are there in CVD process to deposit or to grow the film. The advantage that we have seen in CVD compared to PVD was that it will cover the surface or it will cover the step better than the PVD technique. So, step coverage is better because here the chemicals are reacting at every step. For example, if this is the step, let me just draw it here. If this is the step that you want to cover, this one, and you deposit the material using PVD, what happens is it will get deposited, but this area will not be covered correctly, right. But if you go for CVD, then because the gas is everywhere, it will react uniformly and the step will be covered. So, that is the advantage of CVD over PVD. Of course, there are some limitations as well, because in CVD process the harmful gas needs to be properly addressed, otherwise not really great to use the CVD techniques. That is why it requires a proper clean room environment to use this kind of techniques, particularly when it involves the exhaust gas, which are harmful for the body. So, contribution in terms of biomedical systems, microfabrication is a key step to design any types of biosensors chips to address the problem, and characterization evaluates the fabricated patterns, right. So, this is one part of it where you understand that how the metals are deposited. Now, once it is deposited, what you need to do, you have to also create a different patterns, and how to can you create different patterns by using photolithography. That is why when you say that electronic system design and mathematical aspects, what is within the electronic system design are sensors, and that is why we wanted to after discussing with Professor Chandramani, who is leading the course, we wanted to see that how the sensor design and lithography could help to understand the whole concept correctly. And that is why if you see the slide once again, the lithography which is patterning has photolithography, there is a E-beam lithography, there is X-ray lithography, and then there are characterization techniques which are like DRI or wet etching. So, etching techniques like dry etching and wet etching. In dry etching we use reactive ion etching or deep reactive ion etching. In wet etching we use different chemicals, right. For example, if it is silicon etching, we use KOH and TMAH, potassium hydroxide, and tetramethyl ammonium hydroxide, and you know that this is done at room temperature or 25 degree centigrade. KOH is done at 80 degree centigrade to increase the rate of etching, right, or etching rate compared to TMAH. In KOH the walls that you see are rough. In TMAH the walls that is there, the wall is this one, this wall, right, is smoother when you use TMAH. TMAH is neurotoxic, KOH is not. So, but everything should be used under the wet bench environment with a proper exhaust. So, again, why we are using lithography or why we are learning lithography? Because we want to understand how the patterns are formed. Why we are learning etching? Because finally the sensor is fabricated, right. Now, we go for SEM and TEM. SEM, as you know, is a scanning electron microscopy. TEM stands for transmission electron microscopy. There are other characterization techniques like AFM, which stands for atomic force microscopy. There is ellipsometry, FTIR, XRD, X-ray diffractogram, surface profilometer, and NMR. So, these techniques are used to characterize the material that we have deposited on a substrate. Also, some of the techniques like SEM would help us to understand the morphology of the material, morphology of the design, right. And SEM can be SEM and FESEM, which is field emission SEM, depending on the type of the structure that you want to visualize, not easily visualize, you want to see, which is we are not able to see in optical microscope, you go for the SEM. So, if you see back, the another thing that we have discussed is the simulation, right. We have used COMSOL simulation, and then we have taught how the simulation will work, and we have also showed you the different way of modeling this particular material. Let us take an example of a heater. Then you can see that how the temperatures of on the surface area can be measured by applying a given power, right. And this COMSOL simulation is very helpful, because before we actually fabricate the sensor, if you know the simulation result, then you can adjust your parameters accordingly. So, the functionalization check prior to hardware realization of electronic module is what the COMSOL simulation will help. Of course, there are other softwares also, but we have shown you one of the example of using COMSOL multiphysics. Also, it helps in accessing physical quantities including heat, pressure, stress, force, flow and current. Then once you kind of understood how the sensors are fabricated and how it is patterned, right, how the calibration techniques are there, we move to the application of the entire electronic system. So, what is the application? So, we started with EEG. If you remember EEG, and if you can see on the slide that we were talking about the different regions, right. The frontal region is here, right, exactly here. Then there is a occipital region just at the back, right, where and is used for visualization. Then there is a temporal region, there is a central region. So, there are several regions in the head that are divided into different parts, so as to understand that where to keep the electrode. Now, generally you may have seen that 1020 system is used for measuring this EEG signal. However, for a certain application, right, and of course, you have to have a reference and ground that you already know. For certain applications like neonatal screening, hearing screening, if you apply a given signal which can be your ABR, right, you will be able to see the EEG signals from the frontal electrodes. So, the another technique for measuring the EEG or different audio stimulation, one is ABR, another one is AEP, right, another one is mismatch negativity, another one is positive peak at 300 milliseconds. So, there are several different parameters that one can use for designing this audio stimulation. This is a very important problem because in our country particularly lot of neonates don't go under the neonatal hearing screening because of the lack of the facilities in the primary health center, and that is why if you can develop a band that can be placed on the neonate head and we can tell that whether neonate can hear or may be hearing or may not be hearing, right, and the parents can take the baby to the tertiary clinic, then this testing can be done accurately. The importance of this testing is that if the parents would not know and already the baby is 2-3 years old, that will affect the cognitive ability because the baby cannot hear till 2-3 years, right. It is a speech. Whatever we understand and how we learn is by having our audio and visual and speech all together working, isn't it. So, if I say some word, you are able to process it because you can hear it, but if you cannot hear at all, you will not be able to process it. So, overall cognitive ability may get affected, and that is why very important thing is to understand how to use this multi-stage EEG acquisition circuit to develop this particular band. So, we went into details about the electronic system, but when we talk about electronic system, we have to also talk about electronic module, and when we talk about electronic module, particularly EEG signals, since EEG signals falls in microvolts compared to millivolts of ECG. If you measure ECG, it is about millivolts. If you measure EMG, about millivolts. ECG is electrocardiography and it is from the heart. EMG is from the muscle, electromyocardiogram. EEG is electroencephalogram, that is the brain signals. Now, there is one more called ECOG that we may not have discussed in this particular topic, but ECOG stands for electrocardiography, that is a signal from the brain. This EEG is little bit different than ECOG because EEG is from the scalp electrodes. From the scalp there is a impedance that is provided by the skull, right, and that is why the EEG signals are different than little bit different than the ECOG signals. However, both originates from the brain. So, we understood how to place the electrodes or how to use the electrodes with the head stage and how to use the amplifier, whether it is a broadband amplifier, how to control the signals, how to adjust the gain, and how the band pass filter would work, isn't it. So, acquisition of the signals using the ADC, DAC, processing signals using filters, clippers, clampers, counters, comparators, op-amp based computational circuits, all we have covered in this particular course, and that actually is a core. So, sensor is one part, signal conditioning is one part, simulation is one part, and application is one part, and whole thing is covered by the math, right, because you require a strong math background to process all the other parts, right. Whether you do a theory and then you apply for modeling or apply for simulation, a whole concept comes from your basic math, and that is why this course is of utmost importance to understand the remaining side of this electronics. So, let us go to the next one. You have also seen ECG, right, multi-stage ECG acquisition circuit, in which we have shown how to design the complete electronic module, whether instrument amplifier was there or high pass filter was there, low pass filter was there, or it is a band reject filter or notch filter, half wave rectifier, trigger unit. We have also discussed the how to detect the QRS using this electronic module, and the other part that we have been discussing is on the 3D printing. Now, see now when you say electronic system design, once you understand sensor, once you understand electronic circuit, once you can develop the entire module, you have to package it. Packaging, there are many techniques to do packaging. One of the techniques is 3D printing, and we have been discussing in detail how the 3D printing will work. There are several different kind of materials that one can use, SLA, PLA and whatnot, but the point is the basic understanding about how to create the CAD file, how to store it, what is the requirement, this is what is covered. Absolutely important, because there are two ways of doing it, right. Of course, there are other subtractive machining techniques. Here we are talking about adding. One is subtracting, right. So, subtractive manufacturing, additive manufacturing. So, we have discussed those details. We have also seen how to 3D print or how 3D printing can produce a complex shapes with minimum material usage, right, and ultimately results in optimal form factor. So, that is another part of the topic that we will be discussing. We have discussed. If you see the 3D printing further, that we talked about different technologies, right, whether it is a thermoplastic in a form of wire, or is a light cured resins, or it is powder technologies, and we further discussed FDM, FFF, or we discussed the SLA, UV LCD, polyjet, INA, right. We also discussed CJP, binder jetting, SLS, and many more. So, we have tried to cover as many topics as is possible within this given period. Then we have also understood the integration of the sub module, which is the very important part in the final step of any electronic system development, and validation is also another part, that once you make a system, have you validated the system. And finally, the statistical analysis that will help to prove the system performance, right, or understand. So, we have seen several statistical test, parametric test, whether it is one side ANOVA, two sided ANOVA, PET-T test, Pearson correlation. We have also done the non parametric test, Mann-Whitney U test, Wilcoxon signed rank test, the Krukel's Wallis test, and so on and so forth. So, the point is, when you start, you have to observe, then formulate a hypothesis testing, data analysis, and conclude with that, right. So, we have seen the entire cycle. Again, statistics involve a very heavy math. So, that is the idea. Then we also understood the basic math concepts that are required to understand the time domain, frequency domain, EEG signal, how to process it. So, what do you require for that? We require understanding different type of signals, you understand different type of transfer functions, linear algebra, probability, sampling theorem, time frequency analysis, all these are covered, because this all will finally result in biomedical system, right, from signal acquisition to pre-processing, feature extraction, classification, validation, all the way to the optimization, right. So, now you would, I am hoping that with this particular thing that we are discussing here, you were able to understand that how different dots can be connected together, and can be seen that why you have to learn different topics under the under this course, and how it will be useful for connecting several things. When you talk about electronic system, electronic system does not only mean that you take a sensor, take a 3D printer and put sensor within the 3D printer. No, electronic system design is way complex than it looks like. So, it has several factors into the game. The first one, as I am reiterating, is the sensor design. When you say design a sensor, right, you have to then do the modeling of that, you have to do the simulation of that, you have to fabricate a device, you have to design electronics modules for the same. You understand that the signals should be processed and not noise, what kind of electronic module you design for the same, right, and then entire circuit should be packaged. So, 3D printing, and when you utilize it, right, how the whole system will work. For example, if you want to look at the biomedical robotics, right, you can use the same sensors and use the optimization theory to understand what is the best path, right, to reach to a particular stage. So, that is called path planning. So, this path planning requires a heavy math. So, when you talk about biomedical robotics, or you talk about robots for different applications, right, how to move it, what are different kind of maneuvering mechanisms, this all requires you to have the understanding of math, understanding of sensors, and understanding of the electronic systems. Alright. That having said that, once you learn this thing, you can also look into several other courses that are available in NPTEL. Some of those are fabrication techniques for MEMS based sensors, in which you can further go in detail and see how the etching is done, RI, DRI, that is discussed in detail. There are several characterization techniques. If you look at sensor actuators, we have discussed way more in detail about COMSOL multiphysics, 3D printing system, electronic system for cancer diagnosis. We have shown different kind of staging of cancer, types of cancer, what are different electronic systems that can be designed to diagnose this cancer. And then recently Mahesh has taught a course on the introduction of neuroscience and neuroinstrumentation, where I took few topics to help him out, which is on neuroscience, CNS, PNS, biopotential, EEG, ERP, BCI, microcontroller array development, recent developments in neuroscience and neuroelectronics. So, several things you can further understand and go through, which I believe will help you to get much more familiar to the concept of electronic system design for biomedical applications. So, with that I thank you. I hope that you enjoyed this entire course, and I wish you all the best for your exams. If there are any things, you always can approach the TAs who are working with Chandramani Singh, and of course Professor Chandramani Singh as well, over using the NPTEL forum. Right. Till then, I wish you all the best, and I hope to meet you in one new course sometime in few years. Till then, take care. Bye for now.